All right, today we're going to tackle a problem that, at first glance, looks completely and utterly unsolvable. And then we're going to walk through a pretty revolutionary new way of thinking that finds a perfect, elegant solution where all the old methods just failed. Ready to have your mind blown a little bit? Let's get into it.
So, where do we start? Well, our story begins with what I can only describe as a mathematical monster. Seriously, this is the kind of equation that probably gives mathematicians nightmares. It's a puzzle that has pushed the very limits of what we thought was even possible to solve with algebra.
I mean, just take a second and look at this thing. It's a 13th degree polynomial. It has 14 different terms. And notice the coefficients, those numbers in front of the x's. They balloon up into the thousands and then shrink right back down in this perfect, weird symmetry. It's intimidating, it's super complex, and there is no obvious way to even start.
And that's the real question, isn't it? If someone handed you this in a math class, your first thought might be to just give up. I mean, this isn't your friendly neighborhood quadratic equation. Where in the world do you even begin? Okay, so to really appreciate the breakthrough we're about to see, we first have to understand why the usual tools in the mathematical toolbox, well, they just aren't sharp enough for a problem like this.
The crucial difference here, and this is everything, is between an estimate and an exact answer. For centuries, methods like Newton's method could get you close, but think of it like a blurry photo. You can kind of make out the general shape, but all the fine, important details are lost. And those tiny little rounding errors, they can add up and throw your whole calculation way off. What we're looking for here is the high-resolution, perfectly sharp, exact solution.
And that's what brings us to the hero of our story. When you're facing a lock that seems completely unbreakable, what do you need? Well, you need a brand new key. And this key is Ezouidi's theorem. Now, the wording here is super important. This is not about approximating or estimating or getting close enough. It's a structured step-by-step process, what mathematicians call recursive, which really just means each step builds on the last one. And it's designed to find the exact roots. It just completely sidesteps the problems that have had algebra stuck for hundreds of years.
You know, this quote from the source material really drives the point home. It's a bold claim, right? It's saying that problems we literally thought were unsolvable actually can be solved, precisely and perfectly.
Okay, so we've got the monster polynomial, and we've got our revolutionary new key. So now, let's put that key in the lock and see how this thing actually works.
The process is kind of like being a master watchmaker, carefully taking apart a really complex watch. Instead of trying to force it open, you follow a very precise procedure. First, you reframe the problem using a new set of terms called symbolic coefficients, which we'll just call S sub r. Think of these as a new set of gears that'll help us see how the machine really works. Then, you calculate each one, in order. And finally, you just step back and watch for a pattern.
So we run the first calculation. Now, it's a complicated formula, but the result that pops out is surprisingly simple. It's 0. Huh. Okay. That's interesting. So let's do the next one. And again, after all the math shakes out, the answer simplifies down to 0. And the third one, you probably guessed it, 0 again. Okay, a very clear pattern is starting to show up here. And this is where the sheer power of this method just becomes undeniable. As the calculations continue, every single one of these symbolic coefficients, all 13 of them, simplifies perfectly to 0. It's like all of that complexity, all those huge numbers from the original equation are just canceling each other out inside this new framework. So, what does this cascade of zeros actually tell us? This is the moment. This is where all the pieces finally click together to reveal the answer that was hiding inside that monster all along.
Because all of those symbolic coefficients turned out to be 0, that terrifying 13th degree polynomial just collapses. It simplifies into this ridiculously elegant form. The monster, it turns out, was just a disguise for something incredibly simple. X plus 1 to the power of 13 equals 0.
And once you see that, the solution is just staring you right in the face. The only number you can possibly plug in for x to make that equation true is -1. That's it. That is the exact, perfect, symbolic answer.
But hold on, how can a 13th degree equation have just one answer? Well, this is where a cool concept called multiplicity comes in. Think of it like a key that has 13 identical notches on it. It's still just one key, but it has to fit perfectly into 13 different parts of the lock at the same time for it to turn. That root, x equals -1, is that key.
It is the single, unique solution that satisfies the entire complex structure of that original monster equation.
The journey from that massive, scary equation down to a simple x equals -1 is just incredible. But this is so much more than a clever math trick. So why does it actually matter?
This is why this matters. First, it is all about certainty. In fields like physics or engineering, being off by a tiny little fraction can mean the difference between landing a rover on Mars and creating a billion-dollar crater. In cryptography, an approximation could leave a backdoor wide open for hackers. You absolutely need the exact answer. Second, this opens up whole new paths. It proves that some problems we've just labeled unsolvable might just be waiting for us to look at them from the right angle. And finally, it reinforces the very foundation of our modern world. Precision is absolutely everything.
And that's the thought I really want to leave you with. This problem wasn't solved with a bigger, faster computer. It was solved with a better idea, a new perspective. It really makes you wonder, what other impossible problems are out there, just hiding an elegant solution, waiting for someone to find the right key?